Alright, so this video is going to talk about parametric equations of lines. You guys are used to seeing lines in this format, maybe sometimes in formats like this, like those are all recognizable as lines to you from 2 dimensions, but you can also write them in a different format. And that's writing both x and y in terms of some other variable, usually t or theta. So like one easy way to do it, and it's kind of a cop-out way, is to just let x equal t and then figure out what y is. So like in this one, that's a really easy way to do it, because then like y equals 2t plus 5. You might also see this as a vector, and this really illustrates what the point of a parametric equation is. So a line, you can draw the line. This one's easy. It's got y-intercept 5 and slope 2. If I call that also 5, then I could show that my slope 2 looks like a slope 2, which is good. Slope 2 goes through that point. Okay, so there's a line, but I can also think of this as a moving point. So like here is where t equals 0, right? Where t equals 0, x is 0, and y is 5. And then this vector kind of just shows where the point is. So if I set t equal to 1, then x would be 1 and y would be whatever it is, I guess 7. So this point is going to move according to where that vector tells me to go. So at t equals 0, t equals 1, and then I've kind of introduced a parameter into the line. This t is actually changing depending on where I am on the line. Over here, this will be like t equals -2 or something. So it gives me a little bit more information on the line. Parametrizations are also annoying because there's infinitely many of them. If for some reason I wanted to be annoying, like this was easy, x equals t, right? If I wanted to be annoying, I could have said x equals 3t. Why? I don't know. I'm your younger sibling or something. So it's fine. It still works. I just put 3t in for x. Now I have 6t plus 5 for y. So this looks way uglier, but it's still a parametrization for the same line. And what happens is that now my t values change. So here, this is still t equals 0. But this point, this is now t equals 1/3. Because if I put in 1/3, I get x equals 1, which is what happened when I put in t equals 1 here. So, okay, am I being annoying, or did I introduce a new concept? Because now what's happening here is that this point, it's still traveling across the same path. We still cross the same path of the line, but we cross it 3 times as fast. So like this can be important if your parametrization actually means something. If you're an air traffic controller, I don't know if air traffic controllers actually work with these, but they could. Like these could be passive airplanes, and we could figure out whether they collide. Things like that. So it might matter how fast we're moving through space. Okay, so one important thing to remember about parametrizations in general is that every curve has infinitely many parametrizations, and some of them will look similar and some of them won't. Okay, here, if I wanted to parameterize 2x plus 3y, I could do it the same way. I could solve for y and set x equal to t maybe. Or like sometimes I'm going to do some things that are intuitive. So like what if I thought really hard and figured out that if I put in 3t for x, I could put in -2t for y. So like basically I just need to make 2 different expressions for t that always satisfy this equation. And that's almost always a valid parameterization. Probably in this class it will be. So if I put in 3t for x, let's just try it. On the left-hand side, I get 2 times 3t plus 3 times -2t. So that's a total of 6t minus 6t, which is 0. So that does satisfy this. So that works. If it equals 6, that's a little bit harder. I might still be able to be clever. What if I put like 3t plus 3? and then just negative 2t, that's still going to work. So there, this is harder to be clever with, but I can still sub that in, and it'll still work, I promise. But it only works because it was clever, and you don't always want to rely on being clever. But that's 6t plus 6 minus 6t is a total of 6, so that works. If it's 7, I might not be able to be as clever. I mean, now I see the pattern. I guess this is 3t plus 7 over 2. But like sometimes your best bet is just to solve for y or solve for x, doesn't matter. No variable is more important than the other now. But if I just do that, like this always gives me a parametrization. So that's fine. That's an okay parametrization. If I wanted one without fractions, maybe I'd do something different, but this is fine. Actually, maybe I can't get one without fractions now that I think about it. So, great. Okay, so, and then going backwards, can we go backwards? So like if I start with this, if I start with 3t and negative 2t, how do I get from a parametrization to a Cartesian equation, which is an equation relating x and y? That's a hard question in general. By trial and error is is like, I can be clever in reverse. I could write, oh yeah, if I take 2 times the x plus 3 times the y, I always get 0. I can solve for t maybe, so I might be able to do it algebraically. Let's do that. Okay, so t equals 1/3 x. Okay, that's good. So then I sub that into here, and then y equals negative 2 times 1/3 x, so y equals negative 2/3 x. And then be able to see through algebra that that is the same as y equals negative 2/3 x is the same as 2x plus 3y equals 0. Okay, so that's good. So going back the other way can be easy, can be hard. With lines, it's not so bad. So why do we care about parametrizations? Well, we might care about this moving point thing. That's an interesting concept. In some places, it might just be easier to work with one variable. 3D printing is something that uses parametrizations heavily to figure out where all the points in space you want to print are. I don't know what all the points that satisfy. I mean, I do because I've studied lines, but like if it were more complicated than this, I don't know what all the points that satisfy any given equation are. But if I have a parametrization, I do. I can just keep putting in values of t until I'm tired or done, or if things start to repeat. So they're really good for things that are not lines. But actually, even with lines, when you go to 3 dimensions, then parametrizations can be really helpful. Because in 3 dimensions, I repeat, I can't write a Cartesian equation for a line. Like x plus y equals 5 is a line. X plus y plus z equals 5. This would be going up to 3 dimensions, right? Z is the 3rd dimension. That's not a line. That's a plane. So that's no good. If I'm going up in dimension, I can't use this. There's a thing called symmetric equations that I can use to represent lines in 3 dimensions. It's not my favorite. Basically, it's like it looks like this. That's apparently a line in 3 dimensions where we've got 2 equal signs. I don't want to deal with that. I might just want to deal with a parametrization. Like if I have t, 2t, 3t, that's a pretty easy line to understand. It goes through the origin when t equals 0, and then it moves up more in the y, twice as much in the y as in the x, 3 times as much in the z. So even without visualizing or drawing this, I can kind of think about what that is. That's a moving point in space. Then I don't have to rely on Cartesian equations because I don't have one. That's that's garbage to me. Don't think it's garbage because it is useful in some cases and you'll see it. But that's kind of some motivation for parametrization. We will do more of that in this class.